Hello. In this final section, we will go over just a few more examples that illustrate how exponential um, equations can be used in some certain applications. And we're going to focus our attention on models for exponential growth and decay. So if we let y be a variable changing exponentially with respect to t, where t typically represents time, a quantity of time. And if we let y subscript 0 represent the initial value of y when t equals 0, then equation of this form, y equals y sub 0 e to the kt, can be used to model either exponential growth or exponential decay. And in the section when we looked at graphing of exponentials, we kind of looked at two examples of this, but just a quick rehash here, right? So exponential growth would be like if you have time along this axis and y along this axis. As time increases, you get a behavior like this, right? The quantity y increases as time increases, but the rate of increase also goes up, right? So it increases at a faster and faster rate, right? So things like population growth populations often grow exponentially over time. And then exponential decay, something like this. Okay, this is time, this is y. So as time goes on, the quantity decreases, but the rate of decrease also decreases, right? It decreases at a slower and slower rate. So the way you know whether a formula represents exponential growth or decay is by this constant k. If k is positive, then the model is for exponential growth. If k is negative, the model is for exponential decay. A typical example of exponential decay would be like radioactive elements. They decay exponentially, which means over time the quantity decreases, right? It decays away, but it also the rate of decay also slows down. Oftentimes it's measured in half-life. How much time does it take for exactly half of the quantity to go away, and then half again and so on, right? So what you will observe is that over time the amount of radioactive material becomes less and less, but it never quite gets to 0, right? It kind of exhibits that asymptotic behavior where it gets closer and closer and closer to 0, but never quite gets there. So what we're going to do is just work out a few examples involving exponential growth and decay. We've actually already done a few examples relating to exponential growth using the compound interest. And we'll do one more example here involving compound interest because it's a good application. But specifically, the continuous compounding equation that we've looked at is an equation of this form, right? Oftentimes, depending on the application, we might not use these exact symbols in compound interest. Instead of using y0, we use p for principal. Instead of using k, we use r for the interest rate, right? But it's a model exactly like this. So here's our first example. Suppose that at 19 years old, you win $100,000 playing the lottery. If you would like to have $1 million when you retire at age 67, determine the average rate of return needed under continuous compounding. So remember, the formula that we've been using for continuous compounding is A equals P e to the RT. And we are trying to figure out the interest rate. What we know is that the amount of money being invested, or the principal, is $100,000. Okay. The amount that you would like to end up with is $1 million, so that's A equals 1 million. Okay. you're 19 right now, you want to have the $1 million when you're 67. So the amount of time is 67 minus 19, or 48, right? So you got 48 years for your $100,000 to grow into $1 million. If I plug these numbers in, I'll get 1 million equals 100,000 e raised to the power of t is 48 times r. R is what we're trying to solve for. If I divide both sides by 100,000, I'm going to get 10 equals e to the 48r. And then if I put this in logarithmic form, I will get ln 10 equals 48r. If I solve for r, I end up with r equals ln 10 divided by 48. And plug that into your calculator, you get approximately 0.048, or as a percentage, that would be 4.8%. So you need an account that has a 4.8% interest rate compounded continuously in order for your $100,000 to grow into $1 million in 48 years. Let's look at another example. This one involves modeling population growth. According to a study published in 2012, Burmese pythons are becoming the new top predator in the Florida Everglades. They are an invasive species. They're not native to the Everglades. They were introduced from somewhere else, from Burma. Not very many animals in the Everglades can stand against a python that can grow to 23 feet and weigh over 200 pounds. So the first part of this problem, 20 pythons were recorded as captured or killed in 1995. By 2009, that number had increased to 378. Write a function of the form p of t equals p sub 0 e to the rt to represent the number of pythons captured or killed t years after 1995. Okay. So first of all, p sub 0 here represents the initial number of pythons, right, which was the number in 1995, and that was 20. And this is not necessarily the total number of pythons, just the number that were captured or killed, right? And then the time period, right? So from 1995 to 2009, that is a period of 14 years, right? 2009 minus 1995 is 14. So that means if the function evaluated at t equals 14 is equal to 378, right? 14 years later, that number increased to 378. So I'm trying to come up with an equation of this form. P of t equals p0 e to the rt. So if I take that, plug in the numbers I know that p of 14, when t equals 14, p of t equals 378. P0 is 20. And let's see, what I don't know here is the value of r, but I do know the value of t. T is 14 years, right? So 14r. So I'm trying to find r, which is the constant that represents the growth rate. Okay. So if I divide both sides by 20, I will get 18.9 on the left. 378 divided by 20 is 18.9 equals e to the 14r. And then if I put this in logarithmic form, I will get ln of 18.9 equals 14r. r. And if I solve for r, I will get r equals ln 18.9 divided by 14. And that is about equal to 0.21. Okay? So it says write a function of the form p of t equals p0 e to the rt. Right? So what I know is that in my formula, p0 is the initial number of pythons, the number captured or killed in 2005, and that is 20. R, I just solved for R, and that's 0.21. Okay, so here is my function right here. Okay, 20e to the 0.21t. For the second part here, it says use the model from part A to approximate the number of pythons captured or killed in 2017. Now the way this model is set up, t represents the number of years since 1995. So in this case, t will be equal to 2017 minus 1995, which is equal to 22. So I take 22 and I plug it into my function. I evaluate p of 22, which equals 20 times e raised to the power of 0.21 times 22. Plug that into your calculator and work it out. You get approximately 2030. Okay? So the estimated number of pythons captured or killed in 2017 is 2030. So it gives you an idea of how quickly these populations can grow, right? It was 20 in 1995. 14 years later, it was 378. 22 years later, that had grown to 2030. Lastly, it says, if the ratio of pythons living in the wild to pythons captured or killed is approximately 100 to 1, how many pythons were estimated to be in the Everglades in 2012? Okay. So in 2012, figure out how many years that is since 1995, right? So 2012 minus 1995 is equal to 17. So then I'll take 17 and plug it into my function here. I'll evaluate p of 17, which equals 20 times e raised to the power of 0.21 times 17. And that works out to be approximately 710 snakes captured or killed. But the estimate is that the actual number of snakes would be 100 times more than this. So 710 times 100, the estimated total number of snakes in the Everglades in 2012 was estimated as 71,000 snakes. Okay, and that is a problem when you have a species that is invasive and has no natural predators. There's nothing to stop the population from just exploding and growing exponentially. And we kind of see that here. Okay, and our last example will be one illustrating exponential decay. A sample collected from cave paintings on an archaeological site in France shows that only 2% of the carbon-14 still remains. How old is the sample? Round to the nearest year. And we'll use the model for radiocarbon dating, which is Q of t is equal to Q0 e raised to the power of negative 0.000121t, where Q0 is the original quantity of carbon-14. So we're not given the original quantity, but we are told that only 2% of the original still remains, which means Q of T is going to be 2% of the original, or we could write that as 0.02 times Q0, right? Because Q0 represents the original, equals Q0 e to the negative 0.000121 t. Okay, and now on both sides, I can cancel out this factor of Q0 on both sides, right? Then I'm just left with 0.02 equals e to the negative 0.000121 t. And now the only unknown is t. So if I solve for t, that gives us an idea of how old the sample is. So the next step would be to rewrite this in logarithmic form, which gives me ln of 0.02 equals negative 0.000121 t. And if I solve for t by dividing both sides by negative 0.000121, I end up with t equals ln of 0.02 divided by negative 0.000121. Evaluate that in your calculator and you'd get approximately 32,331 years. Okay, that would be the estimated age of the sample. So that illustrates a few common examples of how exponential equations are used for modeling, specifically exponential growth and exponential decay. So we'll wrap it up here for this section. Thanks again.